Hello, and welcome to another wonderful adventures of the New York City Category Theory Seminar. Today we have David Ellerman speaking to us from the University of Ljubljana in Slovenia.
Ljubljana.
Anyways, David has by far spoken the most at this seminar. I think the first time he spoke here was in 2016. I think this is his seventh appearance on these pages, on this webpage. Okay, David is multifaceted to say the least. He's in math, quantum mechanics, philosophy, economics. He got his PhD from Professor Parikh in the early 1970s in Boston University, but he was also in the University of Massachusetts at Boston, and he was in the University of California, Riverside. That's a big category theory place. And now he's in University of Ljubljana. He's a few from the second talk on, you've been talking about this partitions and quantum mechanics, and it's been a thrill to watch you add to it, and it's very interesting. And now you're talking in general, fundamental in all of sciences, so that's very interesting. Um, Anyways, take it away, David.
Okay, thank you. So, I'm going to talk about a fundamental duality, as the name is there, and I don't know what to call it. It's you can think of it as metaphysics, but it's a mathematical formulation, and this duality turns up all over the place in the exact sciences, and so I want to try to bring out some of that today. This is sort of the bigger picture here, that two sides of the duality can be thought of as subsets versus partitions, or even at a more granular level, it's its versus dits, or dit is a distinction between two things. So at the logical level, it's usual Boolean logic of subsets, and then at the other side of the duality is the logic of partitions, which is something that's very undeveloped and new. Then you have the quantitative version of the logics, which is the quantitative version of a subset is probability. Quantitative version of a partition is logical information or logical entropy, which is different from the Shannon entropy. I'll say more about this later. And then we get into the straight category theory duality, sub-objects, limits, quotient objects, co-limits, so forth, and so forth on down. So I'm not going to get to all these topics. I won't get to biology today, but the just one thing here. The on the it side, we have these two notions which sometimes are helpful: quiddity and halicity. And quiddity is sort of the basic definition of something, but it may not have individuating characteristics. And on this side of the duality, everything, the quiddity also has the halicity, in other words, has individuating characteristics. So the standard example of that in mathematics would be something like the natural numbers or the integers or the rational numbers, real numbers, and all that, which are perfectly definite, so that they have the halicity is there. And that's the algebra part. But on the other side, you get quiddity and without necessarily having this halicity. In other words, they don't necessarily, you have things which are undifferentiated, and the halicity comes later. And that's what we're going to see happening on this right down here on this side of the duality. And the example there, of course, is geometry. The Erlangen program for geometry, you start off with undifferentiated entities, which are still different. So they have quiddity, and then you impose symmetry groups, and that begins to differentiate and create definite entities. So we're going to get into these things as we go. That's just a big picture. So we start with, on the it side of the duality, this is Boolean logic, logic of subsets, so forth. And it's the sort of questions you ask of a single entity. It's existence versus non-existence, in a subset or not here in the picture. And so The its are the elements that are in a subset, and the logic is the Boolean logic. Now, on the other side of the duality, it's dealing with pairs. And so you have a pair of elements. Then the relevant question when you have a pair of elements is, are they distinct or indistinct? In other words, is it equivalence or inequivalence, or the old notions, identity or difference? So those are the two basic types of questions you can ask, a single element or a pair of elements. So the logic of pair of elements is the logic of partitions or equivalence relations. Equivalence relations makes it perfectly obvious that you're dealing with pairs, and then the ones that are equivalent are the ones that are not. So here is an example of two partitions. Here's a partition where the dot and the star are distinct. They're in different blocks of the partition. Here's a case where they're in the same block. In other words, they're indistinct or equivalent. And we'll see when we get to quantum mechanics that this is the way you represent at the logical level superposition, which is the key notion in quantum mechanics, which is why quantum mechanics is on this side, the dit side of this duality. So one question we might ask, if you have these two logic, why did it take so long to develop the logic of partitions? And the reason is very simple, that Boolean logic is almost always presented these days as propositional logic. And that's sort of the special case of the logic of subsets where the universe is just a singleton, one. So you have just the two subsets, zero, empty set, and one. But the more general case, which is really what you need to see the duality, is the logic of subsets, because subset has a dual notion of a partition. So a valid formula in Boolean logic should be defined as a formula that evaluates to the top of the lattice or the universe for any subset substituted for the atomic variables. Then it's a theorem, should not be a definition, should be a theorem that it suffices just to take the case of U equals 1. And then you have the notion of truth table duality, and so that should be the theorem. So if you look at any logical text today, I would be willing to bet it starts with propositional logic, not with subset logic. And of course, what's wrong with that? Well, then you don't see the duality, because propositions don't have a dual, subsets have a dual. And the duality between subsets and partitions is brought out, of course, in category theory. And here's an example of a function, morphism in category theory. The image is a subset of the codomain, and the inverse image is a partition of the domain. So you see there's sort of dual roles there that subsets and partitions play. Or just to quote Bill Levere, he referred to sub-objects as parts, and he says the dual notion obtained by reversing the arrows of a part is the notion of a partition. So propositions have no dual, so you've had this, centuries of development of logic, and people don't even have the idea that there is a dual logic, because he starts with propositions and then quantification theory and so forth, and so you're not looking for this dual concept. I will assume everybody understands that a partition is the same thing as an equivalence relation or quotient set. These are just different ways to look, different perspectives on the same mathematical concept. And as Jean Calaroto would say, they are cryptomorphic. So the lattice of partitions, in other words, just the join and meet, is something that is known in the 19th century, developed by Dedekind, Schroeder, and others, and but only with the lattice, two lattice operations. So if you're going to have a logic of partitions, you need at least an implication, and that was only developed in this century. So no new operations on partitions were defined throughout the 20th century. Amazing thing about the inattention to partitions, which are, in a sense, just as fundamental mathematically as the notion of a subset. So 2010, I published the first paper on the logic of partitions. This was of correctness and completeness theorem in a semantic tableau system of partition logic. And that was, what, 16 years ago. And to this day, there's not been a single other logician publishing in partition logic. People have heard of it, but it's a lot harder to work with partitions than subsets. Obviously, they're, in spite of this dual relationship, partitions are much more complicated thing. So let's
Are you
now.
in touch with Von Pratt? I said, are you in touch with Von Pratt at Stanford?
Of course.
You're good.
Okay. Now let's go back to the its side, the Boolean algebra of subsets. The partial ordering is, of course, inclusion. You have the usual join as just the union, and meet is the intersection. And then you have the implication or conditional here. Now, for the partition side, a partition is a set of non-empty subsets of your domain, your universe, that are disjoint and their union is U. So a distinction is a pair of elements from the universe that are in different blocks of the partition. The B's here are the blocks, different elements. So the set of all distinctions, dit set of a partition pi, its complement in U cross U is just the set of indistinctions, and that's just the equivalence relation. Equivalence relation set of ordered pairs that are indistinct. So, and the equivalence classes of the equivalence relation are the same as the blocks of the partition. So, given this universe set, there is algebra of partitions. If you enrich the join and the meet, in other words, enrich the lattice operations with the implication operation, that was what was never defined in the entire 20th century. So let's look first at the notion of refinement, the partial order in the lattice of partitions, and this goes back to the 19th century again. So sigma is refined by pi. For every block of pi, there's a block of sigma that contains the block. So for every b, if you take b's as the blocks in pi, there is a c in here, if so that b is contained in c. So that means that you could get pi by chopping up some of the blocks of sigma in effect. So that's the partial order in the lattice of partitions. And it's interesting, first of all, that this refinement relation holds if and only if the dit set of sigma is just contained in the dit set of pi. Number one. Number two, the thing you should notice, and I'll emphasize this later on, is when you have the partial order hold between two partitions, you have a naturally defined surjection between the blocks of pi and the blocks of sigma, because every block of pi is contained in a unique block of sigma. So you just map the blocks of pi here. So every partial order in this lattice defines a surjection, and of course in the dual lattice of subsets, every partial order, which is inclusion, defines an injection in the other direction. So you've seen the duality come out here already in these partial orders and morphisms, which will come in a very big role, and we get to the category theory part. So the join of two partitions is just the partition whose block is the non-empty intersections. Very, very simple definition, and that, of course, corresponds in terms of equivalence relations, that the intersection of two equivalence relations is another equivalence relation automatically. And the meet, well, you can find one way to define it is the indent set of indistinctions of the meet is a reflexive symmetric transitive closure of the union of the two indent sets. So we're not going to use meet at all, but that's the definition. Now, the top of the lattice is what's called the discrete partition, and it's where all the blocks are singletons. So everything has been differentiated, as it were. The bottom of the lattice of partitions, called the indiscrete partition, there's only one block, the entire universe. So everything is blobbed together. And the implication, this is the thing that allows us to do partition logic and not just partition lattice, is the implication is the partition that sigma implies pi is the partition such that if a block in pi is contained in a block of sigma, then you turn it into singletons, you discretize it. If it's not contained in a block of sigma, then you just leave it as the block. So in effect, if you think of the discretized ones as like 1, and the ones that are indiscrete or remain as a whole block as 0, then this implication is really just a characteristic function for refinement. And so then it's obvious that when refinement holds, then every block of pi is discretized, so the implication equals the top. And that, of course, is what has to hold for a good implication operation, just like in the Boolean case, the inclusion holds, the partial order holds, if and only if the conditional is equal to the top of the lattice, the universe set. So that's the notion of implication that allows us to do partition logic in addition to partition lattice. So here's a nice picture of the two in the universe of just 3 elements, your subset lattice and your partition lattice, the discrete partition at the top, the indiscrete partition at the bottom with only 1 block in it, and then all the other ones in between. Now the indiscrete partition is called the blob, and it's because in the Hollywood movie of that name, the blob, you see the blob here is absorbing everything that it meets. And that's what the absorption law for partition meet is, that the blob absorbs everything that it meets. So that's why we call it the blob. And of course, this will also get into coming back in quantum theory where the superpositions are, where eigenstates blob together, as it were. Okay, that's the only joke. So hope you understood that. Now, the subset partition, as you know, any formula. So now we have formulas. You can write formulas in a standard language and interpret them in the Boolean algebra subsets, or interpret them in partition logic. And so you can just mimic the definitions going from one to the other. So subset tautology, any formula which evaluates to the top of the lattice and u bigger than 1, if no matter what subsets you assign to the atomic variables, it evaluates by the set operations to the top. So partition tautology is just the same thing, translate over to partition algebra. Any formula which evaluates to the top, in other words, a discrete partition, regardless of which partitions on U are assigned to the variables. And here we take U equal or bigger than 2 in order to avoid some degeneracy. Now, an interesting fact is, take the smallest universe for partition logic, 2, there are only 2 partitions on a 2-element set, the one which combines the 2 elements or separates the 2 elements. So it's like the power set of 1, which also has 2 elements, the 1 and the empty set. And so whenever you do a partition operation on the 2 partitions of 2 here, you have to get one of those 2 partitions, because those are the only 2. And it turns out that these 2 things are isomorphic. So you do the partition operations here, you do the set there operations here, and you'll get the same thing, mutatis mutandis. As a category theorist, I have no idea what category this isomorphism is in, but it is an isomorphism. So whenever you get the top here, you get the top here, and the bottom, you get the bottom. So that tells us right away that every partition tautology is automatically a subset tautology. Why? Because if this evaluates to the top for every universe, it certainly does it for the universe of 2. But that means that the same formula looked at now as a formula in Boolean logic is a truth table tautology, and we know by this theorem previously mentioned that a truth table tautology is the same as a subset tautology. And so every partition tautology is a subset tautology. So but the inclusion is very proper. And as I'll mention later, we don't have a decision procedure yet for partition tautologies. We know every one of them is a subset or a truth table tautology, but how do you single out that subset of those formulas in logic that are partition tautologies? And when you compare it to Hiding algebras or the intuitionistic proposition, there's no inclusion either way. You have weak law of excluded middle is a partition tautology, but not an intuitionistic tautology. And distributivity is intuitionistic tautology, but not a partition tautology.
What do you mean by, you didn't tell us how you define not for partition?
What?
You didn't tell us how you define negation for partition. You told us to join the mean, the implication, but what is the negation?
Yeah, it's the same. It's the same. It's implication to zero.
Okay, thanks.
And more relevant is the relative negation, which is where you have you keep the pi, you keep the consequence in the implication. So you have all the different relative negations, and all the formulas that are relative negations of the same pi in the partition lattice form a Boolean algebra. So you have a natural Boolean algebra that's contained within for every partition you take substituting zero. If you just use zero, it's very trivial. It's just a 0, 1. So mentioning that partition lattice is not distributive, it turns out that Charles Sanders Peirce published a paper in 1880 when American mathematicians were trying to prove that they knew what they were talking about to European mathematicians. He claimed to prove that all lattices were distributive. So Dedekind and Schroeder and others quickly disabused him that you just take the partition lattice on 3 element sets that I showed you earlier. It's not distributive. And so Sanders Peirce, we never knew what his so-called proof was, but obviously it wasn't a proof. Now, it's, as I said, it's early days in in partition logic. Nothing has been published on it in 15 years other than my own papers. And so we don't have a decision procedure. How do you single out those truth table tautologies that are partition tautologies from those that aren't? And we don't have a Hilbert-style axiom system. My paper just had a semantic tableau system. So in any case, that's, I'm checking off here the things that we're covering. So now I've covered, not going into great detail, logic. And this is all published now in a book, Logic Partitions. And 2 major applications are to information theory and quantum theory, which we're going to talk about later on. So let's move on now to the next thing here, which is the quantitative version of these 2 logics. Now, my mentor in mathematics was actually Jean-Carl Rota, and he died very prematurely at age 66 in 1999. And all of us who had worked with him, I worked with him because he was interested in trying to combine logic and combinatorics, picked up parts of his work. And so I picked up where he had developed what he called the logic of a particular type of equivalence relation. And so I picked up on that, and I developed his work. So all that I'm talking about today really came out of this collaboration with Jean-Carl Rota. Now, he was well aware of the duality between subsets and partitions, and he made the key observation that the lattice of partitions for information plays for information the role that Boolean algebra plays for probability. So in effect, so you're saying subsets are to probability as partitions are to information. So that's this parallelism between these two things. So the quantitative version of subsets is probability theory, logical probability theory. That's where it starts. The Boole-Laplace logical probability. So if we know what is the quantitative version of a partition, we would have the natural logical notion of information, which is not the Shannon entropy, by the way. And so that's what we're going to get here. So Boole, in his original book, remember, he developed not only Boolean logic, but the quantitative version. And so the quantitative version of a subset S is the normalized number of elements, remember, dual to distinctions, in S. So the probability is just this normalized cardinality of the subset S. Now, Rota picked up on this analogy, and he said probability is a measure on the Boolean algebra events. It gives quantitatively the idea of the size of a set. We may ask by analogy for some measure which would capture some property turn out for partitions what size is to a set. And Rota didn't have that. And that was, so he was not able to make the next step. But the next step turned out that it's the notion of a distinction or a dit that is the parallel to the notion of an element of a subset. And here's the table that shows that. So here you have the lattice of subsets. Here you have the lattice partitions. So the elements of a subset are the its, the distinctions of a partition. And here's how they are totally parallel. The partial order in the lattice of subsets is the inclusion of elements. The partial order, in other words, the refinement relation here, is inclusion of dits. So you see the parallel between its over here and dits over here. The join in the lattice is the union of subsets. The join of two partitions, its dit set, it's just a union of the two dit sets. So you see exactly, this is of course just the inverse of the fact that the intersection of two equivalence relations is an equivalence relation. The top is the set of all elements. The top is a set of all distinctions. So you cannot distinguish anything from itself, but all distinctions where every block in the partition, in the discrete partition, is a singleton. The bottom, no elements, no distinctions. So we see the complete parallelism between elements and distinctions. So that tells us that's a natural, logical notion of information. Quantitative version of a partition is right here, called logical entropy. It's just the normalized cardinality of the dit set over the normalization, since the dit set is a set of ordered pairs. And then you can work on that a little bit and you can develop the formulas. This is one good formula, 1 minus the probability of all the blocks squared. And this is another version of the formula where it's the probability of the different blocks and where you're actually summing them up both ways. So that gives you the notion of logical entropy. And for just, if you're given just a probability distribution, whereas what Shannon always started with, Shannon never had a measure on a set. Shannon entropy is not a measure at all in the sense of measure theory. The logical entropy is just 1 minus pi squareds, or 1 minus the product of the distinct pi's. The natural picture of it here is you have a unit square with the probabilities laid off on the horizontal and vertical here, and then you're subtracting off all the squares. So you tract off all these, and you then get the half of the logical entropy on each side. So for this one, I pictured the probability distribution is half, quarter, and 2/8 here, and that logical entropy is 21/32. So each of these notions has, of course, a probability interpretation. Probability of S, a probability of one draw from U gets an it from S. Logical entropy is a probability of two draws with replacement to get a dit of pi. So that's the probability interpretation of both. And then the logical entropy of a probability distribution, probably of two draws of getting different indices. Or if you throw a dart at this box, it's the probability that you'll land in one of the two sides, equal sides here, if each point is taken equal probability. So that provides this logical basis for information theory, the notion of logical entropy, and I argue at some length elsewhere that this is the proper notion of information. It tells you what information is. Information is distinctions. Information is dits, not bits. And Shannon himself admitted that he had no definition of information, whereas this gives you the definition. It's distinctions and quantitative version of the logic of partitions. So it's a logical basis for information there. So I'm checking off that. We've covered that with enough detail. This is all in another book, New Foundations, because we're refounding information theory on logical entropy. And so this book goes into extensive comparison with Shannon entropy, all the problems with Shannon entropy, which I won't go into here, and all developed in this book. Now we come to approach category theory, and we're working in the category of sets. So we want to, rather than start with that duality, we want to explain the duality in category theory using these more fundamental notions of its and dits. So let's start by taking a binary relations in a set, which is a subset of product here. It preserves or transmits elements if for each x there's an ordered pair in the relation for some y. So in other words, each element in x has a one or more elements y that are in the relation. Binary relation reflects elements if it goes the other way, if for every y there's an x. So those are two obvious definitions. And a binary relation preserves or transmits distinctions if for every pair in there, if the x's are different, then the y's are different. And the other way around, it reflects distinctions if for any pairs, two pairs in R, if the y's are different, then the x's are different. So these are just definitions in terms of binary relations, in terms of its and dits. So we're now analyzing it's using its and dits to make these definitions. So what's a function? What's a morphism in the category of sets? Well, it's usually said to be a function which is defined everywhere in single value. But if it's defined everywhere in single value, that gives you no notion of duality. So here is the real definition of a function. Defined everywhere just means it preserves elements. And being single valued means it reflects distinctions. So the real definition of a function is a binary relation that preserves elements and reflects distinctions. And then you say, well, what about the other notions? Function that preserves distinctions, well, that's injection. And if it reflects elements, that's surjection. So the standard notion of function, injection, and surjection all can be defined in terms of this preserving or reflecting its or dits. Now, so this is sort of the natural way to define these things so everything works out beautifully. And so then if you just use that old definition, you get no hint of duality. But its and dits gives you now the natural notion of duality. Just interchange its and dits. So it's like in plane projective geometry, interchange lines and points. So let's interchange the role of its and dits in a function, and you get another type of binary relation, which is the concrete relation that is the morphism in the opposite category, which is so little developed. I don't even think it has a name, and so it obviously should be called a cofunction, because in that side things are called co-limit, and so forth. So a cofunction is a binary relation that preserves dits and reflects its. So obviously that's just like a function looked at the other way. So you got and so it's a concrete morphism. Usually people, when they think of the dual morphisms in category theory, they just think of the abstract arrow going the other way. No, this is a concrete binary relation that satisfies, by flipping it, as usual, you translate products into co-products and equalizers into co-equalizers and so forth. So that's using the its and its duality to actually now define the duality, turning around the arrows in the category of sets. And the universal constructions in sets does the same thing: products, co-products, equalizers, co-equalizers, limits, and co-limits. Then category theory makes a jump into abstract category theory, where you assume all these morphisms exist. When you say, well, the category has limits, or has products, then you're assuming the appropriate morphisms exist. In the category set, you've got to find those really. And that's how we found them. The duality by using its and its. But we can do more. So let's now go into some of the specific characteristics in the category of sets here. Now, to get a little bit ahead of the story here, category theory defines naturality, but does not define canonicity. So you have canonical maps all over category theory, and there's no definition of what makes a canonical map. So I'm going to give you the definition of a canonical map. It means a map which, in terms of the given information, reduces down to one of those canonical maps in the two lattices, to the logic. So canonicity means, given information, it reduces back to the logically defined morphisms. Remember the partial order in the Boolean algebra subsets is the canonical injection, and the partial order in the lattice or logic of partitions is the surjection in the opposite direction. And every canonical morphism in the category of sets and all these constructions reduces down to those given the information. So let's now start doing that. Let's start with the partition lattice. The indiscrete partition, the bottom, is refined by all partitions. So the indiscrete is defined by all, including, of course, the discrete partition. So the partial order gives you this canonical surjection here. But remember, this is the partition of singletons, so it's isomorphic to U. And this is the blob, which only has one block, so it's isomorphic to 1. So you have a canonical map from any set U to 1 element set. And this is what makes 1 into the terminal object in sets. So the terminal object comes from this, going back to this fundamental thing. And now let's go to the same reasoning in the other lattice, the Boolean lattice. Each subset is contained in U, and so you have this canonical injection here, and the bottom is the empty set, so it's contained in any U, so therefore you have a canonical injection from the empty set into U, and that's what makes the empty set into the initial object. So there's two dual notions of the terminal object and initial object in sets. Both come from the obvious dual things in the two logics, the two lattices there from the partial orders. Now, so here's the idea. The partial order is inclusion, the partial order is refinement, but that induces this canonical map, which is a injection. Here it's a surjection. Every block in pi is contained in a block of sigma, so you get this surjection here. And that gives us these extremal things, the initial object and the terminal object. Now let's do another thing in category theory, the epi-mono factorization. So any function, the co-image or inverse image is just this partition on the domain, and the image is this subset of the codomain. And so every partition on X is on the domain is refined by the discrete partition at the top. So that means that you've got a canonical morphism from the discrete partition to F, but the discrete partition is isomorphic to X because they're all singletons, remember? And the blocks in the inverse image partition are isomorphic to the points in the image. So that means you've got this surjection from X into the image. That gives you the first part of the epi-mono factorization. And the other part comes from the opposite, the dual reasoning, of course, that the image is contained in the codomain, induces this canonical injection. So here you have it, any map can be in sets, can be factorized into a surjection followed by the injection. So it all goes back to that, to the canonical morphisms here in the logics. So that's the definition. That's my conjecture, not something you can prove since we don't have it's like the definition of computability. But I think you can show pretty easily that all things that we call canonical morphisms in sets use the given information to go back to the logical level and use the canonical injection or canonical surjection. So then I go over co-equalizers. I mean, if this was a long talk in category theory, then I would go into this, but I think you guys can just work this out yourself, where you see starting the information given in the co-equalizer setup, and then you go through the same reasoning here. You get all your canonical maps, you get your canonical surjection onto the quotient here, and then when you want the universal mapping property of this, you do the same thing. So they all follow by tracing those canonical maps back to, given the information, back to the two logics. So canonicity is really just based on the logic, the two logical algebras. So that defines the duality here. Same works for all limits and co-limits. And also, I got a couple slides here which just repeat the same stuff on canonicity. So we have that. We can check that off as well. So that is enough on the category theory. So we started off noting that subsets and partitions dual, but in the end, we developed the logics, and then we showed not only does logical probability and logical information come out of that, but also we can now define where the duality comes from in the category of sets, and that means the same in any concrete category, a set-based category of structured sets, and then that's abstracted into the abstract category theory there. So let's go on now to creation. Well, this is going back to the ancient Greek notions of substance and form, sort of Aristotelian notions, or substance or matter versus form as an information. And so let's take a look now at the two different lattices again, the 3-element set. You can use 4 elements or any of the others. This is simple to look at. In the lattice, the Boolean lattice, think of it in terms of substance and form. It starts with no substance. There's nothing in the empty set. And then as you move upward, you get more and more substance created. So this is like ex nihilo creation, if you think of it as a creation story. But everything that's created is fully formed. So there's no indefiniteness here that's undefined yet. It's all the things come in fully formed. So zero substance, and then the substance increases, and it's all fully formed. Exactly the opposite in terms of substance and form, those Greek metaphysical categories in the lattice of partitions. All the substance is here. A, B, and C are all in the block, but no form. There's no differentiation. They're all blobbed together in the blob. And then as you move upward here, you're making distinctions. So in other words, you're informing the substance with information. Information is distinctions. Remember, that's the logical definition. So you make the distinction here. Now C is distinguished from A and B, but A and B are not distinguished from each other, and so forth, until you get up to the top. So in effect, you get the same top. You get the universe of these three elements all distinguished from each other, but you have two totally different ways to get there. And so if you think of this as a creation story moving up, then they end up in the same place, the universe, as it were. But in moving up in the Boolean case, you start with nothing, so it's creation ex nihilo. Whereas if you move up in the lattice of partitions, you create distinctions. And that means you start with totally undifferentiated matter, and then you make distinctions. Now, one way to make distinctions, when you think of things in group theoretic terms, is breaking symmetries. And this is, of course, you could actually think of the Big Bang in these terms. You start with this totally undifferentiated, super hot matter where there have been no distinctions, and you start making symmetries start to break as it cools down, and story of the Big Bang. So in ordinary terms of what people normally call creation stories, the two types are ex nihilo creation and creation from what is called chaos. So chaos is the where you have all the matter is there, but it's totally unformed, and then things start to form out of that. And that's exactly what's reflected in these two dual creation stories. So we check off creation here. So now let's go into the last one I can talk about here today, the physics. So classical physics is on this side. Classical physics is fully definite, and the states in classical physics are fully definite. So in terms of math, it's like the real numbers, and then you have all the relationships between them. Quantum mechanics is different because it's indefinite, and so the partition is the mathematical form of indefiniteness. Things are in the same block of a partition, are equated, are indistinct from each other. They're blobbed together, and that's the notion of superposition. So we can characterize classical physics as definite all the way down. That's, of course, a play on the turtles all the way down. Leibniz's principle of identity of indiscernibles. If two elements are distinct, there's always some property applying to one, not the other. Hence, if they're indistinguishable, they're the same thing. So that's the characteristic way to think of classicality. If they have the same complete description, in other words, they're indistinguishable, then they're the same thing. Kant had his version of it. Immanuel Kant, everything as to its possibility further stands under the principle of thoroughgoing determination. All possible predicates, insofar as they're compared with their opposites, one must apply to it. So predicate somewhere or other where two things are distinguished, you have a predicate that applies to one and not the other. Now, so that's classical. Now we go to the quantum case. The key non-classical notion in quantum mechanics is the notion of superposition. Everything else, the entanglement is a special case of that. And so part of the key is know how to interpret superposition. And it does not mean, a superposition state does not mean you're simultaneous in two definite states. It means that you're indefinite between two definite states. And the usual imagery in so-called wave mechanics is definitely wrong. That when you add together two waves, you don't get something that's indefinite. You get something that's just another definite wave. And so that is the wrong imagery to use for superposition. And Dirac was completely clear on this. The analogies lend to the name wave mechanics, sometimes given to quantum mechanics, but it's important to realize superposition occurs in quite a different way. In quantum mechanics, And quantum superposition principle demands indeterminacy, not definiteness, but being indefinite, indeterminate. And now the math is the same. We're talking about the interpretation of the math. The math is not wrong. Complex numbers are the natural mathematics for waves. The polar representation, it's an amplitude and a phase. So the imagery is wrong of classical waves, is wrong as an ontology. The ontology, the superposition, is indefiniteness. And you might ask, well, why do you need the complex numbers for quantum mechanics? And one way to look at it is that the complex numbers are the algebraically complete extension of the reals. And so if your observables, your operators, are going to have a complete set of eigenvectors, you need to work in the complex numbers, not in the real numbers. So the interpretation of quantum mechanics as wave mechanics is misleading, is wrong. It's simply an artifact that you need the Hilbert space over the complex numbers for these reason up here, and yet any complex vector, you can think of it as in terms of an amplitude and phase. So the real point in the math, Hilbert space version is really, it's the Hilbert space version of the math of partitions, indefinite versus definiteness. So quantum mechanics is better thought of as the physics of particles in indefinite states, or in other words, superposition states, rather than wave mechanics. So here is an example of superposition where you can give it the right interpretation. You have two eigenstates, x and y, xness measured along here and yness along here. And so any point here is indefinite between xness and yness with certain amplitude there. So that's the way to think of superposition, not like adding two, sine and cosine waves or something together and getting another definite wave. This is something that is indefinite between xness and yness, when thinking of those as eigenstates. Now, you can actually map a lot of quantum mechanics math back into the lattice of partitions if you substitute for each vector in the Hilbert space the support set. Support set is the set which is one, think of the vector, which is one where the coefficient is non-zero and zero where it's zero. So if you have a particle state like here, if you had three eigenstates in your Hilbert space, then it skeletonizes, or think of a forgetful functor if you wish, goes down to the block ABC if alpha, beta, and gamma are all non-zero. Now, when it's a singleton block in the partition, that means you're in a classical state. That means you're in an eigenstate. When it's a non-singleton block, you're in a superposition state. So you get a very simple mapping of the quantum concepts back into just sets, which of course make a vector space over Z2. And if you get a mixture of singleton, non-singleton states, that's a mixed state. It's your normal partitions. You might have some blocks are singletons, some blocks are not singletons. So that's corresponds to a special type of mixed states where the supports are disjoint. So here is the picture. This is the lattice of partitions in a 4-element set. And so all the partitions down here have superposition states in them. So they're quantum. And up here, the classical states where the blocks are all singletons. And this corresponds, quantum theory, to the fully decomposed state of mixed state of eigenstates. And that's basically a classical notion. Now, in the interpretation, and we think of this as like an iceberg where the classical part is above the water. The part which involves the quantum world down here is where you have superpositions. That's like below the water. Now, in terms of the interpretation, the Heisenberg and Shimoni both had this picture where they called the part below the water potentialities. So you had actualities and potentialities. Margenau and Hughes had the same idea, but they called it latency. So things down here are latent, and then they turn into actualities up here. So the only classical part of the lattice of partitions is the discrete partition. So it, being classical, should satisfy something like the Leibniz principle. The Leibniz principle says if two things are indistinguishable, given the complete description, they're identical. And that's exactly what holds for the discrete partition. If two u and u prime are indistinguishable by this partition, then they're identical. And that's obvious because the indistinction set of u is just a set, it's just a diagonal, just a set of pairs. So if two elements, ordered pairs in there, then they're just identical. So the law of identity of indistinguishability has a partition version, and that defines the classical thing, which are the support sets of the completely decomposed mixed state in quantum mechanics. So getting near the end here, want to define, connect all this up to the Feynman rules and to measurement, so-called measurement. Prefer to call it state reduction. And what we see is that superposition and state reduction are essentially inverse processes. That we've seen that superposition takes two definite things and puts them together into indefinite, and state reduction does the opposite. It is an interaction where a superposition state interacts in a way that distinguishes, makes a distinction between the eigenstates in the superposition, and only one of the eigenstates can survive. And that's what we call measurement when humans are involved, but it happens all the time at the quantum level. So here is a sort of pictorial representation using the Feynman rule, how you get from A to B. And so here we have an interaction with a sieve or a grating. Hermann Weyl uses this metaphor in his wonderful appendix to his philosophy of mathematics and the natural sciences on quantum mechanics. He calls it a grating. So if the grating has, see here you have the blob, which you can think of as a superposition of all these different shapes. And if it goes through there, then this sort of grating distinguishes. It's an interaction that distinguishes. So this is a measurement. And so to get from A to B, because these are distinguished, the Feynman rule says you have to add the probabilities of going through each of these to get the probability from A to B. In the other case, where the interaction doesn't distinguish between the eigenstates in the superposition, which we picture here as like a pasta machine where all the holes don't make any distinction, which when you go through, you can't tell, get here. Then the Feynman rule says you add together the amplitudes, not the probabilities, the amplitudes, and then you square it by the Born rule to get the probability from A to B. So this ties up. Now, what is the difference between these two things? It's because this distinguishes, in other words, makes distinctions, information, distinctions. The Feynman rule cements this interpretation of what happens in state reduction is distinctions are made, and that's how you move up in the lattice of partitions. So this, now we tie it all together. Superposition, indistinct between eigenstates, state reduction, interaction that makes distinctions. So only one of the eigenstates is going to survive with various probabilities. And logical entry quantifies distinctions. So measure state reduction, which in terms of the lattice, it's like you're moving upward. You're going from a partition to a more discrete, a more refined partition. So you're making distinctions and thus have higher logical entropy. And this is why so often quantum theorists think that there's some connection between information and quantum theory. Perfectly right once you define information correctly as distinctions. So classical reality, the top of the lattice, emerges from quantum reality by making distinctions. Now this, you can even make this quantitative. So the Luther's mixture operation is here. This is projection valued measurement. So you have a density matrix, which is how you would represent states. Here, the projections are the projections down to the eigenspaces of your observable, and you pre and post multiply this, and you sum it up over all the eigenvalues, and you get the rho hat here, which is the post measurement density matrix. Now, if you look at the density matrix, how do you interpret the elements of the density matrix? Well, every non-zero off-diagonal element is called a quantum coherent, so that's indistinction. So that means those things are like in the same blob if you look at the underlying support set. So that's the quantum version of indistinctions. And so this operation makes distinctions. So it takes those non-zero off-diagonal elements, and some of them get zeroed. So that's what happens. As you make this projection value measurement, quantum indistinctions get zeroed, so the rho JK goes to zero in this new thing if it is distinguished by that observable, which means, of course, it has different eigenvalues, but that observable. So let's measure measurement. Let's measure state reduction. That's here. So the measurement, you've got to extend logical entropy to the quantum case, so it's just one minus the trace of the rho squared is the obvious generalization of one minus the sum of the pi squareds. And so the difference between the logical entropy after the projection value measurement and before it by the Luther's mixture operation is just the sum of all the coherences that get decohered, that get the indistinctions are made distinct by the observable interaction with the observable, and you just add them up, and that's equal. So logical entry measures the increase in information done in projection value measurement. So that ties up our things here in quantum mechanics, and that's all in this book. And this book and the information theory book are available on your usual hacker book sites, which I assume everybody there knows about. People certainly know about it over here in the Balkans. And I would even recommend the site run by my friends in Zagreb, memoryoftheworld.org. And my website is here and my Substack is here. And thank you very much for listening.
Thank you. Let's thank our speaker. Very nice. David, can you read the chat?
I haven't been looking at it.
No. There was 7 things. Can
I
you
guess
read
I
it?
have to stop sharing to read chat.
Okay, so I'll read it to you. Here's the first question. Doesn't the notion of dits implicitly presuppose an observer?
No, dit is relevant to the partition. It's a mathematical notion. So it's all these sets of ordered pairs that are in different blocks of that partition.
Okay. And Ray wrote, note that the partition lattice for 3 elements is modular and not distributive. Hence, the implication can't be the internal Ham, but has to be a weakening of that notion. Anyways, Ray can defend himself.
Well, David also 5 slides after I wrote that mentioned it anyway.
Okay. Ray also wrote, also note that the dit covers the blob just as singletons cover the empty set. Right. Hold on. Okay, Paul Taylor, well, Sammy Holtzum explained the first question, but Paul Taylor wrote, this subject classifier in a topos might be thought of as an observer dual to the terminal object, providing the elements. Okay, so the map from the single object to the omega is what he's talking about. Anyways, any questions? Any discussion?
So I also want asking about the observer. So I once thought that the law of identity of Leibniz always presumes some notion of observer, because you need some mind in terms of German idealism to kind of project the differences. So Is there some kind of ego behind all of this?
No, I mean, the math is, obviously, there's no observer in the math. When you get to quantum mechanics, quantum theorists get into, they jump down a whole rabbit hole of trying to go from where are the actual distinctions made. And Feynman, I mean, obviously my interpretation of quantum mechanics is very much along Feynman's thinking. All the examples Feynman gives of a state reduction are at the quantum level. And the standard one he gives in his textbooks is where you have a particle that is glancing off of the atoms, scattering off the atoms in a crystal. And if the atoms in the crystal, say, have no spin, then you can't tell which one it's scattered off of. So it's like the one here. So you would, to get the scattering probability from A to B before scattering and after, you have to add up the amplitudes because it's not distinguished which one it scatters off of. So the notion of distinction, quantum theory does not assume an observer at all. That's simply an anthropomorphizing of the thing. And if your atoms in your crystal, say, have a spin and they all have a spin up, and then the one that say a neutron scatters off of flips the spin, then you're over in this situation where now you can distinguish which atom it scattered off of by which one has its spin flipped. And then you add together the probabilities, not the amplitudes. And then Feynman gives other examples, but they're all at the quantum level. So Feynman never went down that whole rabbit hole of where is the von Neumann cut or the Heisenberg cut or something between. Observers have not a damn thing to do with it. It's the information that something has been distinguished. So the notion of distinction, as you learn from the Feynman rules, the notion of distinction is a physical concept. And that's something very new in quantum mechanics. Like in classical mechanics, you have force and mass and charge and all that. In quantum mechanics, you have the notion of a distinction, which is not something that humans need to observe. I mean, these quantum state reductions happen all the time, and have nothing to do with whether they're observed or not. So I hope that answers your question. I mean, I don't think it's new that quantum theorists jump down a lot of rabbit holes, and the whole question of, well, where is the Heisenberg cut between the quantum level and the observer, or the observer, or the observer is all nonsense. It all happens at the quantum level, and we may eventually get more and more observable forms of things that happen at the quantum level, like with buckyball superpositions or something. But still, Zellinger is very clear on this, and Zellinger says that the information that is when a state reduction takes place, the distinction that is made then, and by the way, Zellinger also he and Bruckner suggest the formula for entropy, and not the Shannon formula, but the formula logical entropy. So they were onto. They don't have the whole derivation and everything, but they were onto that. And he says the information doesn't matter if anybody observes the information. It doesn't matter if the information is already absorbed in the interaction with the environment or something like that. So it's not even available anymore. It just matters that it was there. So differentiation is a physical thing, and that's what breaks up superpositions into one of the parts that gives you then the reduction of state. Now,
Right, just a simple comment. Is it possible?
sure.
Oh yeah, because I'm seeing Herman Weil in this slide, and I read Herman Weil talks about the ego in terms of German idealisms when he talks about coordinate independence. So I maybe I thought he might also mention the notion ego, the mind, implicit when talking about this kind of differentiations.
Well, I mean, when humans make a measurement, they force a state reduction and they observe it. But as I mentioned, there's nobody observing the thing, the particle scattering off the atoms in a crystal, which reverses the spin of one of them. Then the distinction is made. It doesn't matter a bit whether humans are observing or not. If you want to compute the probability, you've got to add up the probabilities of scattering off the different ones, not the amplitudes. Whereas if there was no change, you could not, I shouldn't say you could not, I should say Mother Nature does not know which one it's scattered off of. If there's no spin to get flipped, then you add together the amplitudes. These are the Feynman rules, and which carries over to quantum field theory and so forth. And so they tell you right away that making distinctions is the key thing. He calls them distinguishings. I call them distinctions. Same thing. The logic of them is logic of partitions. The quantitative version is logic of entropy. Logical entropy is measured by what happens in projective value measurement and so forth. So it all fits together. And so
David,
this interpretation is not sitting alone. This interpretation is part of a whole theory, a whole metaphysics of mathematics that goes over, quantum category theory and so forth. So it's not just sitting there by itself, coming out of my mind. It's part of a whole metaphysical duality, and that's why the name of the talk is this fundamental duality in the exact sciences.
David, while I was listening, all I could think of is non-degenerate eigenvalues. I mean, you have two different states with the same, when you measure it, you have the same, it's in the same partition. It's the same eigenvalue, so you can't make a distinction.
Right. That's right.
You said, yeah, sorry.
And so, for example, this here, the quantum logical entropy, one interpretation of it is this is the probability that if you do the same measurement of the same state, same observable twice, you'll get different eigenvalues. And that's exactly the same as when you in the classical case, remember the interpretation of logical entropy is a probability. In two different draws from the universe, you'll get a distinction of that partition, which means pair of elements in different blocks. So each block is like an eigenvalue, inverse image of an eigenvalue. and that carries over completely to quantum logical entropy, which is the probability in two identical measurements of identical prepared state, you will get different eigenvalues. So the whole thing fits together exactly.
Right. Let me just put it another way. The set of eigenvectors maps onto the set of eigenvalues and makes a partition of the set of eigenvectors.
Yeah. And as you know, a set partition, the set notions have vector space corresponding notions. In combinatorics, this is what are called Q analogs. So just as you have enumeration of partitions, you have enumeration of the vector space version of a partition. Now, what's the vector space version of a partition? It's a direct sum decomposition. And so in the classical case, the inverse image gives you a set partition. In the quantum case, the operator gives you the direct sum decomposition of eigenspaces, which is a vector space, Hilbert space version of a partition. And classical logical entropy is a probability in two draws, you get a distinction. And quantum logical entropy here is the probability in two different measurements, you'll get different eigenvalues. In other words, you'll get something in different eigenstates.
Okay.
All this is developed in the book. Of course, I can't do it all here. But that's what
David,
the book.
one last question. I mean, maybe someone else would, but you pushed entanglement as a special case of superposition, but how would you do entanglement? In other words, two separate objects are entangled if they're in the same partition, or is it
No,
more
no,
complicated?
then you're working with uh,
Superposition.
yeah, I mean, but you're working with pairs of two particle situation. You can
Mhm.
do the same. You can do the same. Lattice of partition, so forth. But the states are states of pairs of particles. In that case,
Oh, let's say I have two different systems.
I mean, you
So
don't have.
entanglement, right?
Yeah.
So entanglement only happens in two different systems. So you have.
Well, yeah, two different particles or more.
Mhm.
Yeah, I mean that's the usual notion of entanglement. I mean
So it's
there
a little
are
bit more.
other
You
notions
do
that
it.
could be called
You
entanglement.
do it in your book, entanglement.
Oh yeah.
Yeah. Okay. Anyways, any
Yeah,
other questions?
Well, I just had a quick one.
even
What
do.
was
See, you have this when you break everything down to support sets. The point is that support sets retain enough of the mechanism of quantum mechanics so you can model quantum mechanics things like the double slit experiment in vector space over two, which I call quantum mechanics over sets, and everything becomes very simple. So it's like a pedagogical or so-called toy model of quantum mechanics is to do it over support sets. And support sets, 0, 1 vectors, add together differently if they overlap. So when you have, because in complex numbers, 1 + 1 is 2, but in vector space over Z2, 1 + 1 is 0. So they're different when they overlap. But the main operations you need to deal with are all cases where the sets don't overlap. And that's partitions. Partitions, all the blocks are different or disjoint. And so that means you can mimic these things as long as you stick to disjoint sets. Same as when you represent an operator, what's it called? The representation of an operator where it's the eigenvalue times the projection thing.
you mean spectral representation?
Yeah, spectral representation.
Spectral theorem.
Yeah, same thing happens in sets, and you can go right back and forth between set concepts and vector space concepts. That's what's done in combinatorics. That's what Rhoda does all the time, and it's called Q analogs. I call it quantum mechanics analogs, and so you get so the obviously the Q analog of a subset is a subspace. The Q analog of a partition is a direct subdecomposition, and so forth, and all that works. So this treatment of quantum mechanics is not just sitting there by itself. It's something that's part of a much larger mathematical metaphysics, or whatever you want to call it, that I've tried to outline tonight.
Ray, you had something else you wanted to say?
No, well, I'll just say it's always nice this week, next week, we have people returning, and I learn a little more every time and understand it better.
I think
Thanks,
we all
guys.
do.
You can get the books for free if you know how to go onto Hannah's archive or even the site I just gave you, memoryoftheworld.org.
Okay. Anyways, let's thank our speaker again. And 1 second, there's one more question. Let me just, before we get to the question, I just want to say next week, Elias Cooper is speaking about algebraic string diagrams and manifest covariance theory. Semi Holzum says, thank you. Is it possible to think of a functor from set to vec with generators of a vector space from the generators? With generation of a vector space from the generators.
Yeah.
I don't know.
Yeah, that's the whole Q analog thing is a much enrichment of just that simple functor from sets to vector spaces.
Right.
Where each subset goes to the vector space generated by by that set.
Okay. Anyways, David, please stay in touch. All right.
Okay,
Okay. Thank you very much. Thank you. Very,
Thanks for having me.
very enlightening. Take care.
thanks for having me.
Take care.